All right. Thanks everyone for joining today's Space Syntax Lab seminar. I am excited to welcome Dr. Sanjay Somanath, who will be talking about individual-centric urban modeling using synthetic populations and activity-based models. His work presents an integrated modeling approach that combines synthetic populations and activity-based models to simulate daily urban life and explore how planning decisions impact individuals in a more nuanced and equitable way. Sanjay is a postdoctoral researcher at Chalmers University of Technology in Sweden, working in the field of computational sustainable design within the Sustainable Built Environment research area. He originally trained as an architect and later moved into renewable energy modeling. His research focuses on developing computational tools to support architects and urban planners in making better informed decisions, particularly when it comes to understanding the distributional effect of planning choices. And during his PhD, he developed activity-based urban accessibility models that bridge theoretical concepts with practical applications by modeling the interplay between the built environment and residents' everyday activity patterns. He also collaborates closely with the Digital Twin Cities Center at Chalmers, contributing there to the development and application of urban digital twins. And before we start, if you have any questions during the talk, please post them in the chat. We will address them at the very end. And with this, I'd like to hand over to you, Sanjay. The floor is yours.
Thanks, Kimon. So thank you everyone for joining this seminar. The work that I'm about to present is from the final paper from my PhD research. I've left a QR code here and I will present this again towards the end. The kind of outline for today is quite straightforward. I'm going to start a little bit by presenting the research context of where I was when I conducted this research, and then go into the introduction, present a little bit the context of the PhD research that precedes this paper, and then I'll get directly into the paper, going through the method, results, and some takeaways and outlook. So about me, my name is Sanjay Somanath. Like Kimon said, I'm originally trained as an architect, and then I went on to do a master's in computational design. And I entered the industry as a renewable energy consultant in the UK. And after doing that for a bit, I started my PhD at Chalmers in the computational sustainable design group. So a little bit about what we do here at the Computational Sustainable Design Group is we develop tools, workflows, and knowledge at the intersection of social and environmental performance of neighborhoods and urban areas. And we primarily focus on the early stages of design and focus we're working with the architects, urban planners, any stakeholders, and try to help them make more informed and equitable decisions. So the starting point for this is during my PhD research, what we looked at was digital tools to make sustainability related decisions. And we noticed that when it comes to the social dimension, if we're thinking of this triple bottom line model of sustainable development, there weren't that many digital tools that actually helped you evaluate the social dimension. So the question we initially started off for the PhD research was, how do you operationalize urban social sustainability through digital tools? And that started off by looking at the conceptualization of urban social sustainability, how it's operationalized, and how is the implementation done. This led to a conceptual framework of urban social sustainability that showed that urban social sustainability has these two main dimensions, one of social capital and social equity. So social equity would be equitable access and availability of social infrastructure, whereas social capital is more emergent and it's seen as a softer theme in the literature. And once you have this framework, when you look at how practitioners in the industry kind of try and operationalize this, is they look at the different themes that fall under social capital and social equity and try and define what social sustainability means for them in the context of their problem or their project, their sites. And it's this collaborative process of defining social sustainability that then leads into the implementation stage. In the implementation stage, you start by defining some indicators that allow you to measure the phenomena that you want to observe. And then our hypothesis was that could it be possible to design computational models that use these indicators and go into these specific definitions of social equity and social capital to try and operationalize urban social sustainability in this way. And that kind of brings me to the next point, which is how do practitioners actually work with urban planning decisions? So you start with an existing condition, and through some intervention, you want to go to a new condition. And the process usually starts with understanding the problem, empathizing with it, defining what the planning criteria is, coming up with different planning scenarios. You create a prototype or a proposal, and then you need to kind of iterate between these steps to finally reach a point where you can test your planning scenarios. And in the process of testing these scenarios, you might learn something kind of inherent about the problems that you're dealing with that allow you to iterate more and come up with new scenarios, learn something about the users of your built environment through this testing, and finally then you arrive to this new condition. And with that context, looking at equitable access, what we then frame the question is, how can transportation models help practitioners evaluate these social consequences? So transportation models have been around for quite some time. So these start with trip-based models to activity-based models. And synthetic populations had been around for quite some time. It's been used in epidemiology research and transportation modeling. But in the context of neighborhood planning, what we wanted to know was, can we use these methods that have reached a high level of maturity to answer some local questions? So using these transportation models, can planners propose scenarios, test them, and learn something about the individuals that are being affected by these different planning scenarios? So with that, it's quite a mouthful, the title, but I break it down into three different components. So there's the individual-centric part of this, where we're interested in seeing how individuals are affected by the different planning proposals. There's a synthetic population part that actually enables the individual-centric approach, and the activity-based models that look at the temporal aspect as well. So throughout the day, you have different needs, and these needs are kind of connected. And how do we kind of integrate all of this into one single urban modeling framework? And that's what this paper is primarily about. So starting with the individual-centric urban modeling, so this is in the context of urban accessibility, the ability of people to reach and participate in activities. And if you look at the literature, there's four primary components. There's a spatial component. This is where people live today. Where do they want to go? So their origins and destinations. There's the transport component. That's the different modes of transport, whether you go by walk, by public transport, bike, or by car. Then you have the temporal aspect. When do these demands actually arise, and when can they actually be satisfied? And then finally, there's the individual component, which is, who are these individuals, what are the demographic characteristics, and how does the demand vary with the different demographic characteristics. And to kind of simplify this, the way that practitioners evaluate accessibility today, for the most part, is by focusing on the spatial component. So the assumption is that you have a location, and at some distance or time from this location, you draw a catchment area, and the assumption is that all the individuals that fall within that catchment area have access to the location. But what ends up happening here is, if you go back to the definition that I presented here, the ability of people to reach and participate in activities, well, we're not really looking at the people here. What you're looking at is the accessibility of locations. And if we start looking into the individual component, it might turn out that certain individuals do have accessibility to that location, but depending on who you're looking at, you might be excluding a certain subset of the population. And that's kind of where the need for looking at the individual-centric approach arrived. How can we develop models that allow us to look at different demographic cross-sections of the population and evaluate how much accessibility they have? So coming back to the three main components that I mentioned, we go next into the synthetic population that actually enables this individual-centric approach. So synthetic populations have, again, been around for quite some time, and the way it's been generally modeled is you have from census data some marginal counts of different demographic categories for any given area. So you would know how many people belonging to different household types and gender in this case are there in a certain neighborhood. But what you don't have is kind of the joint distributions of different variables. And using the synthetic population modeling approaches, what you can do is kind of impute what those missing values could be based on these marginal distributions. And that brings us to a more fuller picture of what these populations look like. And there are different methods to do this. One of the common approaches to do this is using iterative proportional fitting, which is a fitting algorithm that kind of takes these marginals and imputes what the missing distribution is. But another way of doing this is by using probabilistic assignment. So kind of a Monte Carlo simulation that has the probabilities of different demographic groups being present in different proportions, and then you can start assembling your synthetic population. So one example here is along the different demographic attributes that we start assembling for our synthetic population. One is how are couples formed in the population. So our approach to this, inspired from Tuzluglu et al., was to start with different demographic, two different lists of sexes, so males and females, and then we start by sorting them, use a proxy for their age, and then start matching them. So there's many different approaches through which you can create these mechanisms of forming individuals and then households, and then the different ontological connections within these households. And it's described more in the paper, but what we have by the end of this process are kind of coherent household units that also have individuals within them, with the ontological relationships within the household kind of intact. And they satisfy the demographics of the different neighborhoods within an area. And the synthetic population that we developed is for the city of Gothenburg in Sweden at a neighborhood level, or based on the neighborhood level demographics, but down to the household is what we do. Once you have all of these synthetic agents kind of created, we needed a way to organize them in a data model. So we created different we created a data model for people, households, buildings, and houses, essentially, which is a residential unit within a building. Next, we had to look at where are the locations of these individuals. And so for that, we go to the Swedish cadastre and look at different buildings that have that are assigned to be residential buildings. Using different data sets, we determine what the height of these buildings are, and based on the volume and the area per person, we kind of make an estimation of how many individuals or households can exist inside each of these buildings. We also took into consideration what type of buildings they are, whether they are single-family houses, multifamily houses, etc., and tried to make it as coherent as possible. Once we have the synthetic population ready, then it's time to look at what these synthetic agents do throughout the day. And that brings us to the activity-based models. So an activity-based model is the progression of transportation models that originally looked at a trip-based approach of origins to destinations, but then with the availability of more computational resources, what we could do now is we can not only look at origins and destinations, but also the chain of trips that form an activity sequence. So you don't only look at going from home to work, but you also, the trip from home to work is now part of a larger trip chain. And then you can start looking at origins and destinations that kind of update as the person moves along the day. And a core data set for this is a National Household Travel Survey. We used the National Household Travel Survey from Sweden, which has a lot of data on on the respondents of the survey in terms of the demographic characteristics, but also what was the purpose of the trip, what mode of transport did they use, when did they leave, and how long, what was the distance and time taken for travel. What is missing in this, however, is a location component, which is not usually included. So just to give you an insight of what this travel behavior that you can observe from these National Household Travel Surveys, here we're looking at the top 20 activity sequences. So you have the most common one is home, work, home, and then you have home, work, home, then a leisure activity, and then back home, and so on. So you start seeing different activity or different travel destinations, such as home, work, leisure, and grocery shopping to be the most common ones. And then you have picking up and dropping off of children, which will be important as I proceed with the presentation. You also have an insight of the demographic cross-sections into these activities. So you can see by demographic groups, how do these how does this travel behavior change as you change the destination or you change the time of day? You can start observing patterns in the travel behavior. Now, to be able to model all of this, there are other kind of mechanisms that need to be enabled. So one is, how do people actually move? So for this, we had to do a routing exercise. So I started off by using PG routing, which is a Postgres extension to PostGIS, which is a database for spatial data. But that didn't work out quite quick enough. So even though it did routing quite well, and then you can start comparing this to kind of Google Maps and see how well did it do the routing, we had to explore different routing packages. And we tried Network X. Another one is called iGraph. And that's where we settled in terms of performance, that iGraph was giving us quite good performance to be able to do many thousands of routing queries across the population. There are a lot of other routing platforms that we haven't explored. Graphhopper is one, which allows you to set up a server and call an API, which I've learned is quite efficient, but I haven't tried it. But that's something that I would be interested in if anyone from the audience had experience with some of these. But the routing engine is one component, and that takes care of kind of the car-based routing as well as the active mobility-based routing. For the public transportation, we used a really nice package called R5Pi that comes out of the Digital Geography Lab at the University of Helsinki. And what you can do with this is create a travel time matrix at different grid resolutions for an entire urban region. And by setting this up in different ways, you can get pretty good performance out of this as well. Here's a link to a bunch of different query experiments that we did to get the kind of performance that we were looking for in our models. And this is on a GitHub repository. So what the travel time matrix does is it consumes a GTFS specification for the public transport system, which includes trams and buses in the case of Gothenburg in Sweden. And it has a timetable for all the different lines of public transport. And it takes into account a departure window when people actually move from their origins. So in this model, it's a single departure window that's taken into account at the peak travel hours in the daytime. So I think we're looking at somewhere between 7:30 and 9 for the travel window, but you could, in theory, have multiple travel windows to dynamically change throughout the day. For active mobility, one of the requests that we received from the practitioners that we had as our in our user group when we were doing the testing is to have the ability to allow active mobility users to have preferences for routes. And the preferences for the routes were based on proximity to green spaces, impedance, the kind of slope that you have, the distance and travel time. And then the model allows you to change the weights based on this this map that you see here. So what you're seeing here, colored between red and blue, is the impedance that's caused by the grade, the kind of slope, as well as the distance and proximity to green spaces. So it's a composite metric here that's translated as impedance. You can change this in the model when you're using it. And for the remainder of the results, we haven't used these weights because it's quite hard to calibrate the weights to reach to kind of be able to validate these models. And we found that by not including these weights, it made the model assumptions much simpler. And then if the user would like to kind of use the weights, they had the freedom to do so. Once we have the routing mechanism sorted out, the next thing was where can people actually go or where do they want to go? And these are the destinations. And the primary data set for the destinations of different amenities like restaurants, playgrounds, gyms, and so on comes from OpenStreetMaps. We compared the OpenStreetMaps data to Google Maps as well to evaluate how up to date all of this data is. A lot of destinations for public infrastructure also comes from Lantmäteriet, which is a Swedish national cadastre. In terms of locations of preschools, daycare centers, schools, high schools, that comes from the city of Gothenburg. And this was quite important because if you miss a grocery store that wasn't mapped out by OpenStreetMaps in a particular neighborhood, then you very quickly start seeing unrealistic numbers for how far people have to travel to be able to reach a grocery store in time. And then we implemented a gravity-based assignment model for both the job place assignment as well as grocery stores. And this basically meant that there's a trade-off between how far a destination is and what kind of opportunities you have by going the further distance. So in terms of jobs or workplace assignment, it's weighted by the opportunity or the density of jobs in a particular grid. So if you have a destination that has many jobs in close proximity, it has a higher attraction, and therefore people would be willing to travel a further distance. And the trade-off between the opportunity and distance was calibrated based on empirical data that we had from the National Household Travel Survey. With that assembled, what you kind of get on the other end is a simulation on a neighborhood scale for every hour of the day in a particular neighborhood. Here, what you're looking at is the movement patterns of different residents in the synthetic population traveling within the neighborhood. They're also allowed to travel outside the neighborhood, but that's not really visualized quite clearly here. And you can see the peaks in movement during the daytime, and then when people start coming back home in the evenings. And the different colors that you see here are the different modes of transport. In blue, you have the dots for the locations of homes. And then by the end of the simulation, people start returning back home. So the simulation starts at 3 a.m. and ends at 3 a.m. the next day to account for people who have to work throughout the midnight, and it's kind of a graveyard shift. The other outputs from the model, you can look at aggregated outputs from at a neighborhood level. So that's the bottom figure where you have the entire neighborhood amenity demand. So at different hours of the day, what activities are different synthetic agents engaged in. But you can also zoom into individual level activity schedules, where you can have an individual activity where somebody is first at home, then takes a tram to go to school, for example, and then takes the tram back home. By doing this, what we can also do is we can take user-generated activity sequences and plug them into the model and evaluate how residents actually perform in this new neighborhood scenario. And that's quite an important part of how we design this model in consultation with the different practitioners. We ask them, what's the normal way of when you start your planning process? And public engagement was a big part of their planning process. For any public project in Sweden, it's mandatory to have a public consultation phase in your planning process. And what they would do then is they would ask people to do an activity where they would kind of think about what their ideal day looks like, what are the different activities they would like to do, and then you could plug these into the model and see how that activity sequence performed. In terms of results, when we look at individual variables like age and sex, we get a very low error rate because those are quite easy to fit. For some advanced variables, we use machine learning that predicts what the car ownership would be, for example, based on demographic characteristics, and also the primary status, whether they are working, inactive, or in education, for example. And we compared this to other models, like the Synthetic Sweden national model of individuals for Sweden. And the errors are quite within the range that they found with the Synthetic Sweden model. So we go through the different individual variables and kind of catalog the error rates within them. We looked at the joint distributions between different variables and looked at the error rates between them. And finally, to kind of evaluate how the routing mechanism and the destination assignment works, we compared that to the National Household Travel Survey, and we observe some difference in proportion. For example, based on modes of transport, the prediction models often get confused between bicycle usage and public transport usage. So there's some underrepresentation of bicycle users versus public transit users. And while there are different ways to kind of correct for these differences, they require a lot of individual weighting between modes of transport that would make the model assumptions more unclear to the end user. So we've left those model assumptions and weights between modes of transport as they were. In terms of destination assignment, we looked at what's a median travel distance per purpose within our model. So we had education, grocery stores, healthcare facilities, travel back home, leisure activities, picking up and dropping off of children, non-grocery shopping, and traveling to work. I'm going to skip the travel metrics, but that's more for the validation. But in addition to validating the individual counts of these travel metrics, we also looked at the distribution of each of these metrics, and we used an indicator called the Hellinger distance, which quantifies the similarity between two probability distributions. And then we noticed something interesting in the way the model kind of makes assumptions on how people, on the destinations that people travel to. So here we're looking at two distributions of travel distances. So one is on the left side, you have travel for educational purposes, and on the right, you have travel for healthcare. And what you'll see here in this kind of probability distribution, that the actual survey data has two secondary medians, where the predicted synthetic population kind of smooths out those peaks. And one of the reasons why this happens is, at least in Gothenburg, there are two major healthcare centers at different ends of the city. And while the model doesn't necessarily differentiate between these healthcare facilities, making the assumption that all healthcare facilities have equal weightage, so it doesn't really pick up on these kind of local phenomena that you have. And it's the same thing for health educational facilities, that it doesn't differentiate between high school and university education. So you might have many more people traveling to the many high schools that are kind of distributed around the city with short travel times and travel distances. But for the few universities that you have, which might require larger travel distance, these kind of nuanced differences that kind of are there in every city are kind of smoothened out a little bit. And that I thought was quite interesting, how much it matters to have accurate destination data, and also be able to understand why why do you see these peaks in the survey data, and how do we kind of replicate them within the model. Spatially, we looked at evaluating all of these metrics on a neighborhood by neighborhood level. So what you see here is the difference between travel duration and travel distance from the survey data to the synthetic data. In terms of the central neighborhoods, the model does quite well, but then as you start moving to the outskirts and the islands around Gothenburg, you start seeing large differences in kind of travel duration and distance. One, because you have a ferry service that covers the islands to the city, that perhaps are not being covered by the GTFS data quite accurately. So you start seeing the periphery neighborhoods start overestimating how long it would take to actually travel between them. Now, to look at how would practitioners actually use these models, we created an application case by identifying a neighborhood that's currently under redevelopment. So we looked at the neighborhood of Länsmansgatan in Sweden, in Gothenburg, where there is currently a proposal to add new residential buildings. That's 9 multifamily houses, a bunch of different row houses or single family houses, with a roughly 2,000 new residents moving into the neighborhood. And to kind of compensate for the new amenity demand that will come in with these new residents, the planners have a proposal of adding new shopping centers, some preschools to the neighborhood, and increasing the number of playgrounds in the neighborhood. But in addition to this, they also have a planning objective of trying to investigate the potential for a car-free neighborhood or a 15-minute city approach in this neighborhood. So we wanted to see how can this model actually be applied in practice to answer these planning questions. So we developed 3 different scenarios. Scenario A just looks at the amenities proposed in the public document for this neighborhood. Scenario B is, by going through the public consultation phase, we identified the different comments from the residents in the neighborhood. What are the different amenities that they're missing? So they mentioned adult education is one. So we would like to have more, not just preschools, but also high schools or an extension of a university program that could be in this neighborhood. They also mentioned a lack of healthcare facilities, that they would have to travel quite far right now to be able to get to the closest local healthcare center. And then scenario C is pretty much switching from the any agent that currently uses car-based transport is pushed over to the next most likely mode of transport that they would have chosen. So we're looking at A, which is proposed by the planners, B, which is in addition to the amenities required from the public consultation, and C is when you then take away the car-based travel and look at how that affects people's ability to actually fulfill their daily needs. Next, to be able to evaluate how successful residents are, we developed an indicator called a trip completion rate. So trip completion rate is the proportion of people that are able to fulfill their daily needs under some travel metric. So the metric, for example, could be trip distance or trip time. And then we could say how many residents are able to fulfill their daily needs in under 15 minutes, for example. So just to give you a demonstration of how do you actually calculate trip completion rate, here we're looking at a table where you have different individuals along the different rows. You have the demographic characteristics, for example, which age group they belong to, what was the trip purpose that they were heading out for, what mode of transport they took, and what was their travel time. Now, if we start grouping this into a matrix, we count that at least for the age group of 25 to 34, the first two entries, person A and B, they had a travel time of 9 minutes and 16 minutes. So there's two counts of records there, and only one of them was able to travel in under 15 minutes. So the trip completion rate for 15 minutes here is 50%. So that's roughly how trip completion rate works. And now applying this back to the scenario that I mentioned. Let me see. There we go. So here's the map of Lensman-Gordon. You have the existing amenities in gray and all the proposed amenities in black. And then when we evaluate this neighborhood scenario with the synthetic population model, we start seeing the different trip completion rates for the different demographic groups that are able to fulfill their daily trips in under 15 minutes. And the three underperforming destinations are of education, healthcare, and work. While work is quite understandable because people would have to travel some distance to get to their jobs, but healthcare and education were something that could be fixed by making some strategic choices over here. So once we add the kind of leisure activities, schools and shopping centers, we start seeing a slight improvement in the trip completion rate for shopping and healthcare so this was from the existing proposal first in scenario A. So I'm going to have to run that again. Right. And then you have scenario B. Once you add the educational facilities and healthcare, you start seeing an increased trip completion rate in those places. But one of the goals that the planners also had was to have a 15-minute city scenario here. And once you start nudging car users to take the next most likely mode of transport, what you see is even though the travel to work kind of drastically reduces because of not having access to cars, the amenities that were added in the neighborhood for education, healthcare, and shopping still perform quite well because they're within the proximity of their neighborhood. But what you can also do by looking at this on a more broader level is start mapping the trip completion rate over time. So, for example, the 15-minute number, it kind of feels arbitrary to some extent. Like, why 15 minutes for this neighborhood? Can we kind of quantitatively look at, is 15-minute even the right number to have as a goal for this neighborhood? And as you see the travel time increase, there are three distinct phases to this graph. So first, you have an initial ramp up of all the amenities that could be kind of reached within the neighborhood. Then you have a saturation range where you start approaching the point where no more activities can actually be satisfied within the neighborhood. And then you have a long run up and until almost all residents can fulfill their daily needs. And what we see here is it is indeed possible for residents to fulfill roughly 70% of their daily needs within the neighborhood by providing the right amenities. But given enough time, eventually everyone will reach their destinations. And what you can see is with the no cars scenario, it still performs better than the existing scenario uh, by roughly 10 to 15% of trip completion rate within the 10 to 15 minute mark. So some of the takeaways from this model application, the initial question that we asked was how can transportation models kind of help practitioners evaluate the social consequences of the neighborhood? And the way we decided to approach that was using accessibility as a proxy of what we can call successful in achieving their daily needs. And we found that these models can be quite useful if used along with the traditional planning process. So it's not meant to be a prescriptive model, but rather support the existing planning process that practitioners already have to supplement the public consultation phases and the kind of local knowledge that these planners have about their neighborhood. The activity-based model does manage to capture spatial interactions within individual neighborhoods and can also respond to the local changes at a neighborhood scale. And I think what's the biggest benefit of this approach is that you have spatially and temporally disaggregated populations. So you could look at how does the vulnerable population in this neighborhood kind of perform with different planning scenarios. And perhaps the solution to this does not need to be building new things. It could just be adding a new public transport route, adding supplementary services. It could be providing more social infrastructure to help these residents out. Just wrapping up in terms of the outlook, there were a lot of different things that we hoped to achieve but couldn't manage within the scope of the PhD. One was it's the incorporating children's activities within the household is really important for families that do have children in the household because it changes the travel patterns quite significantly for the parents. And even though children's activities are not directly recorded in the National Household Travel Survey, they are captured in their parents' activities. So when you start thinking about picking up and dropping off of children, there's a strategic decision to be made there by the parents on what's the sequence of dropping children off and then picking them up. And this is something that we weren't able to completely capture in a synthetic way. And we relied on sampling from the Household Travel Survey to get these activity sequences. So I think some future work, it would be really interesting to generate activity sequences rather than sampling them out of travel survey. Another thing that I'm exploring now in the postdoc is how can we use these models to look at energy consumption within households to generate synthetic household electricity demand. And also another thing that we thought would be quite interesting is to move from activity-based models to an agent-based approach where we could actually start looking at interactions between the different agents within the neighborhood. So could we start looking at capacities of destinations? So it's not just that you can have access to them, but there should also be an availability of this amenity, whether or not stores get crowded or if you need to go further to find something that has capacity for you. And along the same line is it would be interesting to explore how different neighborhood plans could support improving social interaction between demographic groups that haven't been able to, that don't necessarily get the opportunity to interact. And I think there's been some interesting work here with urban co-presence that has come out since this work. And I think those are some interesting directions to kind of explore beyond this. So thank you so much. I'm sorry I went a little bit over time, but I hope we have 10 minutes left for any questions. I've left some QR codes here for the model paper. You can also look at the repository. It's on GitHub. It has, I've tried to maintain some coherent documentation if anybody would like to go in and try and apply these or build on these models. Yeah, so thank you.